my name is Rebecca Widdison, and for mini paper 2, we have been talking about DNA damage and the repair mechanisms used to fix it. And for this particular video, I'm going to be talking about nucleotide excision repair. And the first thing that we need to know about NER is that it's used for bigger, bulkier damage, like multi-base damage caused to the DNA that has caused like a disruption in the helix and just the entire replication problem. And a lot of those bigger damages and problems are caused by UV light damage, which causes pyrimidine dimers, and also just like chemical reactions and just a bigger damage to the DNA. And here I showed a normal strand of DNA with just normal strand, and then it shows the UV light coming in, and then it comes in and causes a cross link in between these two bases, which adds a covalent bond, which changes the shape of the helix and can halt DNA replication or transcription from happening, which is not good. That's not what we want. And there's 5 main steps to nucleotide excision repair. And the first step is that on your DNA strand, you need to be able to recognize where the damage is. And then after you have the damage recognized, then you need to come in, you need to verify that that is correct damage, and then unwind the DNA. And I'll explain the proteins that do this after. But in class, he was talking about how in nucleotide excision repair, it kind of comes in, you sit on the DNA, you sit on the damage, and you cut from end to end. So you cut out a bigger part of DNA, and then you come in, you resynthesize the whole strand, get the damage out, fix what was wrong, and then after that, a ligase comes and seals up what has been unwound and what has been resynthesized and fixed. In the last clip, I kind of went over the steps, but here's just a deeper look into what is really going on behind the scenes in all these steps. We have the difference between bacteria and eukaryotes, and in bacteria we have the proteins UVR A through D that kind of gets us through the first 3 steps: recognizing, unwinding, verifying, seeing the damage, and then we have DNA polymerase that comes in and fills the gap and then seal it up with ligase. And in eukaryotes, it's along the same lines, except there's just a few more proteins that are involved in the steps. Like we have XPC and RNA polymerase that recognize the damage, XPA verifies, XPB and XPD unwind. And then for cutting out the damage, we have XPF and XPG, and right there, when it sits on it, cuts that off. That's when we get the 3', 5' exonuclease activity going on. And resynthesizing, we have RPA, our DNA polymerases, RFC, pCNA, and then once again, we seal up the DNA with our ligase. In the next part of the video, we will be comparing and contrasting base excision repair to nucleotide excision repair. And to just start, they are both mechanisms that repair DNA damage. However, base excision repair is smaller damage, more like single base repairs that need to be fixed, and nucleotide excision repair is bigger, bulkier damage. And these damages, NER is more damage to the helix, whereas BER is non-damaging to the helix. So NER is just overall more of a bigger problem in the DNA, but both are still important damages that need to be fixed. And some of the diseases that come if they're not fixed, like NER, we have xeroderma pigmentosum or Cockayne syndrome, and for BER, we have colon cancer. So they are both extremely important. They're both sealed by ligase. However, the mechanisms are a little different. BER is nicks in the backbone, whereas NER is that big cut of the DNA damage that we have coming out. And BER is mainly caused by oxidative or alkylation damage, whereas NER was caused by UV light and chemical damage. And they're both sealed by ligase, and both mechanisms are extremely important. They're just used for different parts of DNA damage, whereas the main thing is that this is smaller damage and that this is bigger damage that we are fixing. For nucleotide excision repair, there are a few diseases that come along with it if it's not working correctly, and one of them that we have is an autosomal recessive disease called Cockayne syndrome. And what Cockayne syndrome is, it is a mutation in the CSA and CSB that affect the transcription coupled NER. And so what that does is that it makes the proteins in NER unable to go in and repair the DNA damage on an active gene. And so because it's unable to do that, it causes a lot of buildup of the damage that's often caused by UV light to our skin and just to our DNA and our overall genome. And some of the side effects of Cockayne syndrome are accelerated aging, growth failure, kyphosis, and in some of the more extreme cases, it's a short life expectancy. And that is it. Thank you for watching my presentation on nucleotide excision repair.